All right, let's get started. Welcome back, everyone. Welcome back from spring break. We've had 2 weeks off. I hope that you guys are all well rested and have been working hard on your projects. We've been receiving updates from some of you, and we appreciate that. We've got a really special guest here today. Before we pass it on to our guest, I do want to update you guys on Sherry. Sherry's actually at LPSC this week along with Jessica. So they had a chance to meet some of our La Space Academy students. If you or any of your team members happen to be popping into LPSC, they'll be there all week and they would love to meet with you. Sherry is actually at a poster session right now presenting, and I see that she's joined us in here. So Sherry, I'm going to make you a co-host just in case you are able to pop in, but she'll at least be observing and listening to us. She's with us in spirit. So Sherry, good luck at your poster session. Hopefully everything's going well. I'm sure it's noisy down there, so it's going to be hard for her to join us or unmute herself. But in the meantime, we've got another great session for you. You know, we've got Teddy here from JPL. He's a robotics. Teddy, what is your official title here? I had it
Robotics technologist, but
robotics technologist. There we go. We're really excited to hear from you, Teddy. We want to welcome you to our La Space Academy. Teddy's rearranged his schedule to be here with us tonight, and we greatly appreciate it. And without further ado, let's actually just present Teddy and hear what he's got to say for us. Thank you.
Great. Thank you all for having me today. Excited to share with you guys a little bit about Mars Helicopter. So I guess this is my first time using this application. I'm not sure how interactive it is, but I'm assuming some of you guys might be already aware of what Mars Helicopter is. Is that correct, or are we going in cold?
Well, let's go ahead and do this. So let's ask everybody in the chat. And can you see the chat right now, Teddy?
Yes.
Okay, so in the chat, if you're familiar with Mars Helicopter, go ahead and type. And just so you know, Teddy, after you're done with your presentation, we'll have an opportunity for students to ask you questions. We've got an interactive platform where they'll be able to text questions and you'll see them pop up live.
Okay.
And you'll get to see that. So it's a little easier to read than the chat flowing through at 100 miles an hour. But yeah, so we've got some that know a little bit about it. So it gives you a little.
Sure. So for those of you who aren't familiar, in 2020, we're sending a new rover to Mars called Mars 2020. And part of that mission is going to be the Mars Helicopter Technology Demonstrator. So we're sending a brand new rover, and on the belly pan of that rover, there's going to be a little helicopter strapped to it, which is our baby. And it'll be the first time that we're going to fly a powered flight on another planet. So we have a team at JPL working on it. We've partnered with AeroVironment, who's helping us with the mechanisms, and we're all extremely excited to get this underway in the next couple of months. Actually, we're coming up to our ATLO, our final integration with the rover, and then next year we launch. So we're very excited, and currently we're in our final integration stages. What I'll be presenting today is a little bit of a backstory of how we got here. But before we get into the slides, I guess any questions about why helicopters? Any questions for me directly? Otherwise, I'll just get right into the slides.
Well, we actually do have one already that popped up. Kristen English, who wants to know, how do you actually command it, or how does the rover, or does the rover have some type of programming to command it?
Great question. So helicopter dynamics are extremely tricky even here on Earth, and there's no chance that the helicopter would be controllable remotely. It's all autonomous. So all of its guidance, navigation, control functionality, all of its flight software stack, it's all encapsulated inside the helicopter. We do have a data link back to the rover, so we can send information back and forth either during or after a flight, or loading flights up before. But once we start spinning blades, we're all autonomous.
Awesome. How about how big is it? Are you going to talk about that in your
Why
presentation?
why don't we dive in? Let's
okay, sounds good. And our students know that they can, either hang on to their questions for the end, or they can, kind of add them in the chat. And as you're talking, we can help monitor that for you as well. So in the bottom middle of your screen, you can click the share button.
Okay.
And once you click share, you can just double click on either your screen or your PowerPoint presentation.
It says host disabled participant screen sharing.
Oh, I'm sorry. I had made you a co-host, and Let me see. Let me do that again. There we go. You should now be able to share.
All right. Okay. Share. All right, let's see if this works out. I'm also going to try, so I have some videos. Should I share computer sound so you guys can hear the videos?
Yes, please. That would
Or
be
will
great.
we get in a weird echo loop where you'll be hearing?
No, it should
Okay,
actually just play the sound off your computer.
understood.
Mhm.
All right, let's give this a shot. So can you guys see my screen?
We can. We see your like presenter mode. So if you hit, there you go. Perfect.
Great. All right. So let's dive right into it. You guys see the video and hear what's going on?
Yes, we can.
Great. So we'll just start off with this little video clip showing what our
Starting off with a bang. That was an awesome video.
Yeah, we got
Coming to a theater near you, somebody
put
said.
a lot of effort into that music. So that's the vision, that's the dream. But first, we'll start off with why. Why are we doing this? Why are we trying to put a rotorcraft on another planet? Adding the aerial dimension to our robotics capability or our autonomy and exploration capability on Mars is really going to open up the opportunities that we have for different types of science, for different types of stratigraphy, mapping. You pick a category of science that happens on Mars, and what we think is that by adding the aerial dimension to it, we'll be able to either explore further, faster, more efficiently. There's also a very obvious use case, which mirrors a very common use case here on Earth, which is drones acting as a camera in the sky. More specifically, a scout for potentially for future human manned missions on Mars, having a helicopter scout be able to fly over the ridge, get some really high quality resolution images of the next ravine, or just for a network of rovers or a network of scouts onto themselves. Being able to fly around on Mars, you'll be able to map an area much quicker than you can with a rover. A helicopter can move at meters per second, whereas the rovers are much slower than that. There's also inaccessible areas. There are physically inaccessible areas that rovers just can't get to because of the mechanics of a rover, but there's also biologically sensitive areas that we would never send a rover. So potentially in the future, there may be regions where we can send a Martian rotorcraft and have it fly over this biologically sensitive or interesting region that we think something might be happening with, where a rover would never be allowed to get its tracks dirty there in the mud. So how do you do it, right? How do you fly a helicopter on Mars? I guess I'm curious what the spread of interests are or degrees in this group in terms of how many controls people or aerodynamicists or mechanical engineers. But just from a broad picture, flying a helicopter here on Earth is hard. On its own, it's very hard. Now, if you suck all the air out of the atmosphere and you're left with 1% Earth's atmosphere, imagine trying to produce a gust enough to give yourself a little bit of lift. That's one of the reasons why it's extremely hard to fly on Mars. So, there's the long distance, so we can't, great question earlier, we can't do teleoperation. Everything must be autonomous. The 1% Earth's atmosphere in terms of density makes it extremely difficult in terms of controllability to stabilize a helicopter and then also be able to have enough bandwidth to do the types of maneuvers that you need to fly forward, catch yourself, react to a gust. What that means is we need to have very large blades spinning at very high RPMs and a very light vehicle to stand any chance of producing enough lift to get up off the ground. Mars's gravity is 1/3 that of Earth, so it's actually a benefit. It makes it a little bit easier to fly, but overall it's a bad trade, right? It's having 1% the atmosphere and 1/3 the gravity is a pretty tough challenge. And the temperature, that's the other tough part. You'll notice there's no tether in this image. We're fully autonomous, not only in our compute and our autonomy capabilities, but also in terms of our energy and our energy budget. One of the biggest challenges that we've had to go through is figuring out how we're going to survive the night. Negative 90 degrees Celsius is pretty cold. And, there are parts of a helicopter that it's okay to get, the blades cold. The carbon fiber, if you work out the coefficient of thermal expansions, making sure that everything kind of expands and contracts uniformly, you're fine. But there are other parts, like lithium-ion batteries, that don't do so well in the deep cold. So we need to heat ourselves, actually. Part of our energy budget is reserved for surviving the night every single night and making sure that we can heat our batteries throughout the night. And like I was saying, other parts like the legs, the blades themselves, that's okay if they get cold, but our internal battery, some of our key avionics and embedded systems, we want to make sure those stay within a specific temperature range. Now we have batteries, but that also means that we're going to have a solar cell. So above the helicopter itself, we have a rectangular solar cell that allows us to remain self-sufficient and recharge right after we're done with the flight, recharge so that we can get enough juice to get to the next day. So those challenges were kind of distilled down into what we call the 3 commandments. The first being very low weight, so less than 2 kilograms. The second being we need to spin at upwards of 2,000 RPM. And part of those, another wrinkle to that requirement is that, if you have the space to grow, you want to make your blades as big as you can. You get more lift, but you need to fit underneath a rover, so you can't get too big, and you need to make sure you can fold up in a configuration that allows you to be deployed from that rover. So then you get a little bit smaller, but you still want to get as big as you can until you run into the fact that the tip of your blades are going to start getting close to the speed of sound on Mars. So the blade tip Mach number was also a requirement to keep that below 0.7. As you get closer to 1, more challenging aerodynamics start affecting you, and your control starts being affected by that as well. So that was another one of our design kind of requirements out of the gate. So this is a little more detailed view of what a Mars helicopter looks like. 1.2 meters in rotor diameter, that's from tip to tip. Starting from the top, we'll work our way down. And I'm not sure if you guys can you guys see my mouse?
Yes, we can.
Yes, we can.
Great.
Sorry.
So starting from the top, we have our solar panel, right? And that's hooked up to charge control circuitry, and its function is pretty self-explanatory. Keep our batteries charged or charging during the day so that we can survive the night and have enough juice for flights. We have 2 sets of coaxial blades. Now, regular helicopters here on Earth usually might have 1 blade or several sets of blades rotating in a disc. And then to counteract the blade torque, there's usually a tail rotor. There are benefits and disadvantages to each design. We went with a coaxial design for several reasons. It allows us to shrink the body of the helicopter to essentially that gold cube that you see underneath. And we can get additional lift out of having 2 stacked rotor sets. Again, folding is a consideration, right? So trying to keep the entire volume of your spacecraft as small as possible is critical. Moving on down, for those helicopter enthusiasts among us, we have a fully actuated swash plate, so collective and cyclic control on each rotor. So that means not only are the blades, we're controlling the speed of the blades, but we're also controlling the angle of the blades in 360 degrees of rotation. Now, if both blades just feather, plus 2 more degrees after a command, then you'll get more thrust per revolution. But you could also periodically or cyclically change how you feather those blades, and that's what allows the helicopter to tilt and move sideways, forward, and back. And we have that controllability on both the upper rotor disc and the lower rotor disc, each of them with their own brushless motors. And then we get to the heart, brains, soul of Mars Helicopter, which is our avionics cube, or what we call it, the ECM, electronics control module. Inside there is where we have all of our batteries, our power conditioning systems, our CPU, microcontrollers, and FPGAs to help us get through the mission. We also have sensors, cameras. So we have an IMU, so accelerometer and a gyroscope. There's no magnetometer because it wouldn't be of use to us on Mars, but we do have an inclinometer to give us a better sense of where down is. And then we have a black and white downward facing imager peeping out the bottom. You're not going to be able to see it in this image, but poking down the bottom, we have our black and white imager, and that helps us with feature tracking. So our navigation filter, our state estimation system, takes in both the inertial sensors. So if you were to close your eyes and move about a room, you have an idea of where you are, and it's really good for high rate updates, but not so great in the long run because you drift. So you take the benefits of high rate sensors and the benefits of imaging sensors and fuse those together, and that's how we come up with a navigation solution. Then I guess, some more obvious things. We 4 sets of legs that are pointing down, and I was referring to the thermal problem, or challenge rather, but the CO2 gas gap insulation is essentially multiple layers of insulation around our electronics, and Mars' atmosphere is just essentially going to fill that and give us effectively a little bit of a blanket to help keep our batteries warm. Any questions about the layout or what we're looking at here?
Well, we do have a couple questions in the chat. So has the hardware assembly fabrication begun for the helicopter yet?
Yes.
Alec wants to know.
Yes. So the flight model is built, and we are currently in the process of, we've actually finished our test campaign with the FM. So woo! We wrapped up our FM test campaign at JPL a couple of months ago now, I think 3-4 months ago. And great success. We're all very excited, all very proud. But now we're faced with the final humps essentially to get over, which are testing with our deployment system. So there's a separate team working on how do you get the helicopter out of the belly pan of the rover, how do you deploy it, get it on the surface. So we're testing with that deployment system right now. And then eventually we're going to get into ATLO, which is final assembly and test in our high bay clean room at JPL. And then finally we make our way over to the Cape, hop on the rocket, and then we'll be on our way next year.
Wow. So Jorge wants to know, so is the speed of sound not supposed to be surpassed?
Yes, it is advantageous to not get anywhere near it. When your blade tips start getting near the speed of sound, you'll start producing the same sorts of shock waves everyone sees in like Top Gun movies, stuff like that. Those shock waves are real, and it makes controlling a helicopter a lot more challenging. So that's why staying below Mach number of 0.7 helps, just firewall yourself away from that challenge.
Cool. Mithiel wants to know, I'm not sure if you covered this, but what type of materials were used for insulation?
So one of the really cool things about Mars Helicopter is how much off-the-shelf equipment we use. So a lot of the electronics and components are off the shelf, but some of the other more interesting things aren't like the crazy, you've never heard of space age kind of material. The blades are carbon fiber. The legs are carbon fiber. The insulation, we have Mylar, layers of Mylar that help us insulate. And there's special coatings that you can put on there to help reflect the heat back. But yeah, nothing too crazy there. The textbook methods for how to insulate yourself. If you've ever gone to marathons out in the cold and you see people wrapping themselves in these metallized sheets, similar to that.
Cool. And that kind of connects with a little bit with what John's asking in terms of how resilient the blades are as far as staying balanced with wear and tear and time.
Interesting question. So balance is extremely important with any rotorcraft, and especially when you have larger and larger inertias with a 1.2 meter diameter and you're spinning at 2000 RPM, keeping those blades balanced is very, very important. In terms of maintaining the balance, that's an interesting one. Never had anyone ask the wear and tear aging effects of the balance of the blades. Now, the easy answer is we're only there for 5 flights. So our mission is 1 month, and inside that 1 month mission, Mars helicopter is 1 month. So the rover is going to drop us off, and then for a period of 1 month, they'll stay within radio earshot of the helicopter, so they can take pictures of us. They can send radio data, radio traffic back and forth. And in that 1 month window, we only need to execute 5 flights. So any concern about wear and tear would really be for longer term effects.
Got it. We'll do one more and then we continue with your presentation, but this is kind of a combo, 2 questions. Adam and Tyler, why'd you choose a helicopter as opposed to a tail sitting plane? And also, why wouldn't you choose a quadcopter?
Interesting, very interesting. So the tail sitting plane, great question. There are actually other research efforts that are working on tail sitters for Mars. So it's a design that has some definitely considerable merit to it, and would also work on Mars. There are benefits and there are pros and cons to each approach, right? With a helicopter, with a coax, you could sit still, right? So in terms of your guidance, navigation, and control complexity, right, there are the challenges of how do you stabilize in 1% atmosphere all of the crazy dynamics that are going on, all of your circulating air currents, all of your, any gust of wind. There's those control problems. But if you were to simply say, hey, we just want to just hover in a position and take a photo from a guidance perspective, that's much simpler. Whereas if you have I'll first talk about a fixed wing, and then a tail sitter is kind of somewhere in the middle, right? So whereas a fixed wing, you need to always be moving, right? So it lends itself to different scenarios. However, you may get better efficiency trades with fixed wings, because it would require less energy to glide than it would to just constantly be fighting gravity. Conversely, with a helicopter, or let's go with the multi-copter. So I think you said a quad or a hex. Those are also viable designs, but now you start running into challenges of packaging again, right? So if you want to move to a multi-copter, you could go multi-copter of 1.2 meter blades, but now you're a much larger vehicle. So you could scale it down and do a multi-copter of much smaller blades, but now you're playing these efficiency games again, where you have much tinier blades spinning, and to get the same amount of thrust to lift, let's say, the same mass, you're going to need to spin those blades much, much faster, right? So tinier blades spinning faster are going to have different efficiency trades than 2 sets of larger blades spinning at a comparatively slower speed. Again, you can make infinite little modifications. And actually, there's aside from the tail sitter concept that I know is currently being worked on, there's also the future follow-on work of figuring out what's the next version of Mars helicopter being considered, and that's actually a project that I'm working on, where we're trying to propose a hexacopter, or at least a multi-copter design, but we're thinking 6 right now. And again, that's serving 2 different needs, or 2 different regimes of operation. Definitely higher mass, higher weight, higher complexity also in terms of moving parts, right? Now, you look at a stacked coax rotor system here, and you have a swash plate on each, so you have 3 servos per motor, 6 servos total, plus your 2 motors, right? So you have 8 actuating elements there. So it's not dead simple. But compared to, let's say, going to 6 blades, each of them having a single servo for pitch control. Now you're at 12, right? So it's all a matter of trade space. You can make a tail sitter work. You can make a glider work on its own. You can make, obviously, we've made a coax work here on Earth in our testing environment, and we, knock on wood, we hope that everything works out for the 2020 mission, and we'll be flying. And we're currently analyzing, how to make hexacopter work. It's all doable. It's a matter of what you're trying to achieve.
Awesome. Well, thank you for answering those questions, and I guess we can, proceed with your presentation.
So, enough CAD, enough modeling. This is what the engineering design model of Mars Helicopter looks like. This is full scale. So no tricks, no fake kind of actuators or anything like that happening here. This is a full scale 1-to-1 replica of the flight model. I wish I had a couple more days to prepare. There's a version of this slide deck with photos of the flight model, but I wasn't able to get that through our unlimited release system as quickly. But promise me, believe me when I promise you that it looks exactly the same, give and take. So starting from the top, again, I'll just highlight some cool things. So this is our solar panel. That's the motor for the upper rotor. This was a hand-wound motor, actually. I don't know if anyone's into RC airplanes or anything like that as a hobby, but this is a hand-wound 3-phase brushless DC motor. And then we have our swash plate here, and you can see it's actually tilted at an angle. That's the whole point of a swash plate. It's a bearing. It's a bearing system that allows 3 servos to dictate what its angle is. And that's how you affect the pitch of your blades. Then we have our lower rotor system. So lower rotor motor, the lower rotors, lower swash plate, and then you can see the 3 servos around. And then we get to the guts of our baby, which are our avionics boards. So there's four sides, so it forms a cube. And then in the center of that cube, we have our battery system. Now, I mentioned before commercial off-the-shelf parts. Our compute element uses the same processor that's in most of all of our phones. ARM, Qualcomm-based CPUs. Excuse me. The microcontrollers, all COTS microcontrollers. And how many of you are familiar with vaporizers? The things people smoke. Those use 18650 lithium-ion battery cells. That's what's powering Mars Helicopter, 6 18650 cells. Now, those cells are also used in power tools and a bunch of other devices. But anytime you'll see one loose hanging around, not in a battery pack, that's usually where it came from. But yeah, COTS off-the-shelf lithium-ion battery packs. Our compute elements are off-the-shelf as well. And then just moving on down in this image, you can actually see we have a Vicon system attached. That was just for the engineering design model in terms of verifying that its navigation system was working properly. So we flew the engineering model inside of a vacuum chamber, which we'll get to in a couple of slides. And we're using the Vicon system to validate that the helicopter is actually where it thinks it is. Any questions about what we're looking at?
Well, I see in terms of recording video, will it be able to actually record video? Mario wants to know.
So we have a color imager and a black and white imager. The black and white imager is facing down. It's hard to see in this image, but right where my mouse is where we have one of the camera sensors. So the black and white imager is facing down to get good feature tracks as we're moving along on the surface of Mars. And then we have our color imager, which is the same camera that's, again, in our cell phones, that's canted forward slightly. Our goal is to take pictures with the color imager. In terms of video, that's one of our stretch goals, not put down as our base one, our level 1 requirements rather. The requirement, the purpose of this whole thing is to prove that we can fly. Anything on top of that is cherries on top. So the rover, we're still working out all the details, but we hope that the rover will be able to take pictures of us flying, while we're in midair. We're definitely going to be taking pictures. Whether or not we can get video, I guess depends on the frame rate. So that still remains to be determined.
Cool. So Rush wants to know, how are you deploying the helicopter?
That's a great question. So I cannot show that slide animation again because I haven't gotten that one released, but I can give you a really cool hand demo here. So if you imagine my left hand is the belly pan of the rover, the way the helicopter is stowed, so if my finger is the central axis of the rover, it's laying on its side and it's attached to the bottom surface of the rover. When we get to Mars, the rover is going to be driving around carrying us along. And the first thing it's going to do is drop, when it's ready to deploy us, the first thing they'll do, there's a dustpan covering us just to make sure we don't get dirty. It'll drop the dustpan off, drive forward a little bit, and then we're sitting sideways, so it needs to rotate us right side up. And while we do that rotation, our legs are actually going to deploy out. So in this image, in the engineering design model, we did not have the hinges in the legs, but on the flight model, we have hinges that allow the legs to rotate to the side and rotate up, so that we can fit in as tight of a volume as possible. So when we do the final deployment, we get rotated, the legs splay out, and then the rover will drop us. There'll actually be it's called a frangibolt. It's a very carefully designed bolt with a shape memory alloy actuator that heats up, and as it heats up, it expands, and eventually that bolt gets stretched, then it pops, and when it pops, the entire helicopter will fall. It'll fall upright, land on its legs, have a little jump, and then the rover will drive over us, get to its predetermined position, get ready to start recording, and then we'll start our mission.
Wow. And how long is each flight session that you're doing?
So
Vincent wants to know that.
Great question. Each flight's going to be 60 seconds to 90 seconds.
Okay.
And that's dictated by our batteries. We need to make sure that by the time we land, we still have enough juice to get through the night in terms of heating. We could definitely fly longer if we were only in there one and done, but we want to get our 5 flights in. We want to make sure that we could extend the longevity of the battery to get us through those 5 flights and survive every single night during that month. So yeah, 60 seconds to 90 seconds. And to quickly summarize those, the first flight is going to be takeoff, hover, land. Then we'll all go party and have a great time. Then we'll come back the next day, and then we'll start stepping up the difficulty in terms of takeoff, maybe translate, come back to your original location and land, and then we'll build from there.
Okay, neat. A couple were curious about the winding, like is it hand wound, or how long does it take to actually wind it?
The motors?
I think so, yeah.
Yeah, so the motors were hand wound using square wire to increase its packing density. I was not involved in it, but I just marveled once I heard the details about the engineer who did make them. And so the rotor system, so the servos and the actual brushless motors and the rotors themselves, those were made through our partnership with AeroVironment. So there's an engineer there who spent the time and hand wound each rotor, and I think, if I remember correctly, I forgot how many pole pairs there are. There's upwards of 40. I think there's I thought it was 49 last time I checked, but upwards of 40 pole pairs, 3 phases, but yeah, all done by hand. Extraordinary work.
Awesome. All right, well, do you want to proceed?
Yeah.
And then we'll take some more questions in a bit.
So after
Teddy, we can't hear you.
Okay. So let's try that again, this time muted. You guys hear me better now?
Yes, definitely.
Great. So now that you saw the magic, I'll try and unpack what's going on. First, let me pause. So the room that we're in right now is called the 25-foot space simulator, building 150 at JPL. And just about everything we've made on lab has gone through this building at one point or the other. And what makes this building very special is that it has two very interesting capabilities. The first is that it can simulate any atmosphere you'd like. So you can pump down to extremely low pressures, essentially get to a vacuum, to flush out all the contents of whatever the air that happened to be in there that day. And then you could carefully backfill with specified volumes or specified ratios of whatever you'd like. For our situation, we wanted to backfill the chamber to achieve a specific density that will match what we will experience depending on the time of year that we land on Mars. And so we pump down, get all the air out, backfill with carbon dioxide to match the specific density that we need. And there's another capability of this building that we didn't use for good reason, but other tenants of this building have used many times in the past, which is that it's also a solar simulator. So what you cannot see in this image, about 50 feet above the helicopter right now, there's a massive mirror. And to the side of the building, there are these, I think, 35 kilowatt bulbs. There's only like 35 kilowatt bulbs that shine an incredibly intense light up to the surface of this mirror, and then allow you to beam that energy back down onto whatever it happens to be in the chamber. And that's extremely useful when you're trying to send things out into space. You want to make sure that with all the heating and cooling cycles that something will experience, that nothing will break. For our purposes, we only cared about the pressure, right? We were using the 25-foot space simulator to simulate the atmosphere on Mars, but that was only half the equation. We also needed to simulate the gravity. So that's not, there's no magic anti-gravity happening here. What you may be able to see, though, is a string running right along here. And that went also about 35 feet into the sky to an I-beam. And in the center of that I-beam, we had our gravity offload system, which is essentially just a high-tech fishing reel. And its job is to tug upwards with a constant force so that with 2/3 Earth's gravity, so that what the helicopter feels or experiences is that 1/3 remnant, which brings it back into what it would experience on Mars. So we're simulating the gravity, we're simulating the atmosphere, and that's how we could prove to ourselves and prove to the project at large that yes, this thing will actually work. So this was a momentous day for the team to have the fully built engineering model fly on its own under its own power. There were prior versions of the helicopter that didn't have a battery pack, that were being sourced. The energy was coming from external supplies. This was the first time that we proved that the thing can actually, yes, fly on its own. You will see some harnesses underneath. Those are just ground support harnesses to allow us to charge or discharge or monitor the battery remotely. And then also we have several e-stop kind of kill signals that go into the helicopter. So I'll just briefly narrate. We spin up to our 2200 RPM, climb to 1 meter. We were able to lock in that position very tight. We were extremely happy with that. And the flights are just going to be a sequence, a set of sequences essentially, where we'll say, do this, now do this, now do this. So as you read it off the screen, that's essentially what the helicopter is actually doing in its flight stack. So we take off to 1 meter. We have our heave controller get us to that position. Once we're within our error bounds, then we transition to the next state. We tried slewing 1 meter to, half a meter to the side. And what you'll notice is that the helicopter's a little bit tilted right now. It's leaning a little bit to the side. That's because it's fighting the restoring force of the gravity offload system. On Mars, it would, move to the side and just hang out there nice and straight. Come back to the center, and then we do our landing at the end once we finish our pirouette, and then we come back down. So yeah, like I said, this was a great day for the helicopter team. Really, a full D&V of the design, of the concepts, of the software, the hardware, you name it, that this was a full-up test. At the end, we did 13 free flights with the engineering design model, over 86 minutes of cumulative runtime. And I'll remind you, what we're trying to baseline for Mars is 5 90-second flights. So, really hats off to the mechanical engineers, to the control engineers, everyone involved to make that possible.
Well, and that actually kind of connects with one of the questions here in the chat. So Vincent wants to know, how does the atmosphere affect the heating up and cooling down cycle of each motor after each flight when you're testing?
Great question. So you want to keep the motors as cool as you can. You don't want those to overheat. And the fact that the atmosphere in Mars, the temperature of the atmosphere at Mars is going to be pretty chilly compared to Earth is a great thing. But it's only 1% the density. So even though if you were to sample the average kinetic energy of this volume, you'll find, oh yeah, it's pretty cold. The amount of heat that volume of air can wick away from your heat-sensitive components isn't that high. And we ran into that actually several times when we were testing with the flight model, going down to Martian pressures, and we would do thermal cycling, and we would try and do a run, and we'd run into issues where because we were operating at ambient Earth temperatures, but at Martian pressures, we were overheating very easily, right? So it's very easy to build up heat in your battery pack, build up heat in your electronics, and then we would have to wait an extended period, hours for the thing to cool down, and then we could start back up again. Again, that's what happens when you start a test at 25 degrees Celsius as opposed to negative 25 degrees Celsius. So it's definitely a better for some things like your heat-sensitive components, but it's worse for trying to keep your batteries warm overnight.
Awesome. Well, let's go ahead and continue. Well, before we do, actually, Kristen had a question about that room, the testing room. Can this room get cold too?
Yes. So, so this room, do you see these black lines around the perimeter? So there's a circular room, obviously, right? And then there are these fins. These fins are how the room can, there's actually several layered systems that allow the room to get cool. But yes, you can get very, very cold in this room. And we also did a series of thermal tests with the flight helicopter going cold as well. And the way that happens is you flow, you have these fins running the full length of the 50-foot chamber, right? And each fin has a tube at the center that allows you to pass fluid through the center to cool the entire chamber. There's also, when you get down to the very, very low pressures, the complexity involved in how do you cool something down, or how do you remove molecules from the volume of interest to drop the pressure even lower, gets even more complicated. But that's just a long way of saying, yes, we could definitely cool the chamber down, and we did. And our tests worked out great. Very cool chamber. If you guys are ever in the area at JPL and you guys do one of the tours, if you're lucky and you know someone that can bring you up there, let me know if you guys are in town. I'll be happy to give you guys a tour. But yeah, 150 is a extremely cool and extremely impressive facility.
Nice. All right, well, we can go ahead and continue.
Sure. So yeah, next stop, Mars. So opening up new doors for different types of exploration, right? So we've done orbiters, we've done landers, we've done rovers, right? What we're trying to do now is expand that horizon. So what we'll be doing with 2020 is a rover paired with our Scout, our helicopter. We hope to take some really, really nice wide area, high resolution images. And for the future, right, we're looking into, is there interest, would there be value to just having independent helicopter systems or multi-copter rotorcraft, essentially, systems be deployed to Mars? And once you think that that's a good idea, taking even one step further, would it be worthwhile to send fleets, right? Being able to explore entire regions at a time instead of a single area at a time. And I mentioned earlier the biologically sensitive zones. That's also an area that you know, we think Mars Helicopter, or rather not Mars Helicopter, future Martian rotorcraft might have the edge in exploring. And that's pretty much it. So you know, obviously I want to mention it's not just JPL and Caltech, but it's AeroVironment, our partners in crime. None of this would have been possible without AeroVironment. They've, you know, poured their hearts and souls into Mars Helicopter, and amazing people to work with. And we've also had extensive help from NASA Ames and NASA Langley as well. Great help, great partners. And you know, none of this could have been accomplished over the last couple of years without having, you know, everyone firing on all cylinders from every team, from every sort of engineering or science or you know, subdivision of engineering you can think of. So yeah, I think that's all I have. Yeah, great.
Awesome. Well, we do have some additional questions that have been popping into our virtual interactive chat. Before we do though, Sherry's back in her room from her poster session, so she's now unmuted. So Sherry, you want to say hi to Teddy while I set up the questions?
No, that's fantastic. I did catch. I was streaming your presentation while I was down at the poster session at Lunar Planetary Science Conference. So just it looked fantastic. I do have a quick question for you though. In terms of our students, they're actually planning concepts that are around a secondary payload, a ride-along payload, kind of like what Mars Helicopter is.
Okay.
2020. And I also heard through a secret source that you guys are planning a next version helicopter already, from maybe one of your partners that I heard that from this last but I mean, it's exciting because I do think this really opens up a whole avenue of exploration, and the pilot that you all are doing is just amazingly just fantastic in terms of opening that line of exploration. Had you thought, I know it's a very small payload, but you were talking about those astrobiologically, or you know, the keep out zones, the
right.
The name occurred, the sensitive zones anyway, that may have astrobiological kind of you know, possibilities. Have you thought at all about a tertiary payload of a small probe or something that could be, say, dropped on an RSL that was clean and be able to again?
It's a great question. Yeah.
You know, is that in the works at all?
So I'm actually working on Mars Science Helicopter. So I'm the principal investigator for the Mars Science Helicopter systems task that we have going on at JPL, and we were just awarded that funding last year, about 6 months ago. And that's exactly what we're working on. Essentially, we got a bunch of scientists in a room, and we said, "Hey guys, assume or just dream for a second that there's a bus in the sky on Mars. What would you do with it, right? What are the payloads that you would want, and what would what are the payloads you would want, and what would the missions look like? How could you weave together a cohesive rotorcraft design that could cherry pick? We'll go with the point spectrometer, or we'll go with the high resolution imager, and then maybe an arm, right? Figuring out what combinations of payloads would make up a cohesive story. And we came up with three independent science missions, actually. And currently we're in the process of chasing down our favorite one. And over the next 2.5 years, the purpose of Mars Science Helicopter is to build an Earthbound demonstrator vehicle and prove the ConOps of the mission. So we're going to try and beg, borrow, and steal our way into as many engineering model or off-the-shelf payloads as we can, because we do have a much more humble budget since we are just a research task. But the dream is at the end of those 3 years, we're going to take the rotorcraft out to the desert. And you guys know that commercial from Staples, the easy button, right? That's what we're trying to do. Sequence up a science mission, hit enter, and have the rotorcraft take off, fly to an area of interest, actually do the science interactions, whether or not it's imaging, whether or not it's putting a probe somewhere and taking a reading, whether or not it's brushing away some top layer dust so that you can get some higher level sensing, and then come back home or land at a new location, right? And then at the end of that, have all of that data streamed over to a scientist's laptop back at JPL, right? And essentially just let the machine work, right? That's the dream. At the end of those 3 years is to prove that CONOPS is viable, and really try and stoke the flames for the science community to get excited about it.
Well, that sounds fantastic. I'm old enough to remember the first time they were trying that with rovers, doing those kinds of remote operations that, look, we could actually operate a rover. That could be a mission that part of the or whatever. So back in the Pathfinder days, that was like such new territory. So it sounds like kind of the same sequence. And, you know, for the special regions and planetary protection, I would think it'd be a lot easier to cleanse a copter or a small probe to be dropped on, say, a reoccurring slope lineae or someplace that may have astrobiological interest than it would be to send and land a whole spacecraft.
Right. Yeah.
Decide if it's worth sending a big spacecraft.
Now, I will preface that with I am not a PPCC engineer, and I have good friends that are, and I know that I should not be making claims about what's easy and what's hard to keep clean.
True.
But in terms of total surface area or just volume, right? Yes, you know, it's a reasonable first cut to statement to make that, you know, the less surface area that you have, the less total volume you have.
And they're actually going to be hearing from a planetary protection officer in the academy here, coming up, somebody from headquarters. So, you know, getting them to think about and knowledgeable that there are special regions that if we're looking for life, we want to make sure that we have all our ducks in a row in terms of what kind of claims and readings we can get and how clean they are. Right. So that's really important. And I'm not saying it's easy, but I just, you know, I'm thinking in terms of Mars and any kind of exploration, but especially Mars, it would be, there's so many areas now that have some significance that would be the tantalizing, moving the needle on finding life.
Right.
Those kinds of regions, we have to find a way to access them.
Right.
So I'm excited about your project for that.
Thank you. So I'm happy to hear that. So are we. You know, and we're a team eight engineers right now. So we're trying to move quick. We're trying to move fast, and really try and prove that the idea can work.
So how long have you been doing this? How long in your career are you from starting your career?
Sure. So at JPL or in general? In
general and at JPL.
Sure. So I graduated back in 2012. Then I went back for grad school for a master's. So since 2013, been working at a couple different locations. MIT Lincoln Laboratories, worked on the Perdix drone there, and then dabbled a little bit in startups with the Drone Racing League, which does exactly what it sounds like, NASCAR for drones, and trying to develop the technology and infrastructure to allow us to deploy a race anywhere in the world, right? And then invite the best drone pilots to that location and put on one hell of a show. So worked at Drone Racing League for a little bit, and then also Samsung, and then finally came over to JPL about 2.5 years ago, I think. Yeah, just about 2.5 years I've been at JPL, and I've been loving it. It's it's hard to put in words, but it's my dream job. If I were a billionaire and I had nothing else to do with my life, I'd still show up just because I wake up and I get to work on a Mars helicopter. What's cooler than that? So at JPL, worked on Tango. It's called the Torque Racing Drone. If you guys want to Google it, it's Tango on Racing Quadcopter. So taking Google's best visual inertial odometry system, marrying that with our UAV control capabilities on lab, and trying to make an AI drone that can beat a human pilot. So that was a lot of fun. And I put AI in quotes because everyone has their own definition of AI. But so that was a lot of fun. And now Mars Helicopters, the love of my life, and then Mars Science Helicopter, slowly ramping up on the back burner.
Well, it's funny because you remind me so much of the crew that actually tried the Mars Pathfinder mission, where it was just a bunch of younger career people that were willing to say, this is something new and we want to try it. And everybody's like, well, we don't want to risk our career on that. And so those youngsters, those early career people at the time were Rob Manning and Richard Cook, and the people that are now in charge of a lot of what's going on. And Rob has been on the Academy as well and talked about EVL in the past with some of our teams. And but that enthusiasm and the we think we can do it kind of attitude is where we got now, having rovers land on Mars that are metric tons, not just the tiny little Pathfinder rover. So who knows what rotorcraft future we have in terms of the kinds of things you'll be able to do and make that significant contribution. That's pretty exciting.
Yeah, we're all extremely excited, but we can't lose the forest and the trees one step at a time.
One step at a time.
We still have Atlo to get through, and we still have a lot more integration, but hopefully everything works out. And summer, we're thinking, I think it's February or summer of 2021, between there, will be the first time we fly.
All right. And that's going to be pretty exciting. So go ahead and get back to the questions if you want, Dan, or do you want me to do it? Whatever you want to do.
Yeah, well, let me actually display them on screen so Teddy can see that. And so I know one of the questions I see was from Kristen. How did you get where you are? And I appreciate you kind of sharing a little bit of backstory in terms of your career.
Yeah.
So let's see. Let's look at these questions. Can you see them, Teddy? You feel free to pick one out, or we can do that for you as well.
Yeah, they're moving too.
Yeah, they are.
So yeah, how did I get to where I am? Pick something that it sounds cliche, but honestly, pick something you're passionate about. If me and all of my teammates at Mars Helicopter, no one asks us to stay late. No one asks us to work weekends. We do because we believe in the dream, right? We want to see it happen. And if you're working, if your job allows you to be in that mentality, then hopefully the luck will follow after that. And I've been extremely lucky. What else have you? External copters for other planetary bodies besides Mars? Yes. So not myself personally, but there are other studies and other efforts.
Oh, sorry about that. Somebody somehow unmuted themselves. You guys could mute yourselves, please. That would be great. Sorry about that. Here, hang on tight. Let me just mute everybody, and then I'll unmute you, Teddy.
All right. So other planetary bodies. Titan. Titan is a buzz with interest right now in terms of sending a rotorcraft there. Titan's awesome because it's extremely dense. So it's very easy. Sure, there's some buoyant force as well, but it's also very easy to just stay aloft because the air is so dense. It's more like swimming than it is flying. So check out Titan rotorcraft. And there are a couple of different organizations working on that. What else? Do air currents help keep the solar panels clean? Yes, we hope so. In a coax, in any rotorcraft system, you're going to have circulating air currents, especially when you're near the ground. You'll get ground effect. But it's a double-edged sword. When you're taking off, imagine there's a layer of dust. The really cool thing about having a swash blade is that you can control your blade. You can control your blade pitch to be 0. Spin up to full speed, so you have your rotor disc inertia up to exactly where you want it. And then when you're ready to take off, you're spinning at full speed, but there's no lift yet, right? You flare your blades up and you hop up off the ground very quickly. And the hope is you hop off quickly enough to not allow a circulating current to form and then start depositing dust in your solar panel. So taking off is great because once you get up in the sky, you just catch yourself in the sky and you're good. The landing is a little trickier because you want to land as quickly as you can to not have these circulating currents, but you can't land too fast because then you'll break something. There are studies that have been completed before my time at Mars Helicopter. I should also say, you know, I was not at Mars Helicopter from the get-go. Bob Balleram, the chief engineer, and Mimi Ong, the project manager, you know, they started this going several, I think 3 or 4 years back now, and the concept's a little older than that. So when they started looking into this, I think one of the kickoff projects or one of the side research efforts was actually the dust, figuring out what does the dust do to our, if dust does deposit on the solar panel, how does that affect the solar panel charging? But also if there's just dust in the atmosphere, let's say it's not depositing, but if it's just in the atmosphere, and now that's blocking a little bit of the incoming sunlight, right? That's also going to attenuate your charging capability. What else?
Awesome. We have time for one more.
Okay.
Let's see.
So I see a question about the resin. I don't know about the resin. Sorry about that. Are FPGAs used in the controls of the helicopter? If they are, what are they being used? Okay, great question. So the FPGAs, there's a single FPGA, and that's controlling 2 microcontrollers. And the hope is, you know, if one microcontroller has a hiccup, we can swap. But the FPGA is what we're using when we want to be. It's essentially our central control system, if you will. Everything needs to go through the FPGA. So the FPGA is hooked up to the motor controllers. The FPGA is hooked up to our, you know, Linux running Qualcomm chip, and the FPGA is hooked up to the microcontrollers, which are then hooked up to our low-level, super high-rate sensors. So all of our data traffic is being networked through that FPGA. What else? Each plane. What made me move to each place that I worked? What pulled me there? I'm an East Coast boy. I grew up in New York, born and raised. Went to school in Boston, and then went back to New York just because I love New York so much. Love being around family and friends. But the reason I moved out here was for JPL, not because I had not because I had a special interest for the West Coast or anything like that. I probably would be on the East Coast still if it weren't for JPL. But I saw the position come across, and I couldn't turn it down.
Awesome. One final question I have for you that came up earlier in the chat was, how can we get a hold of you after this? And not that they're going to be emailing you, but maybe can they follow you on social media, maybe Twitter or Instagram?
I wish I was cool enough to have like a I don't. I think I have a Twitter account, but I haven't touched it in years. So you can look up my last name, and you'll probably find like a Teddy Zanetos or something like that on Twitter. I'm happy to answer questions on email. If you guys have questions, you know, feel free to send them across. I can't promise an immediate response time, especially the next couple of weeks. I'll be on business travel.
What they can do is just email us if they have questions for you, and we can, you know, forward you questions or something.
Otherwise, you can find me on LinkedIn too and message me there.
Awesome. Sounds great. Well, Teddy, thank you so much. This was really, really great.
Thank you, Teddy, so much. And thank Mimi as well for getting you all on board. And I'll probably be seeing you at JPL Open House if you guys are going to be having that amazing helicopter out on display again.
Oh, I'm sure we'll have it out there. I'm not sure if I'll be there. I'll try, but I'm sure the heli will be there.
All right. Well, thank you again so much for coming and bringing us this amazing project. And lots of thank yous in the chat like crazy.
Thank you. Cheer us on in 2021, please.
Oh, we will. We will
be watching.
I'll be in the front row cheering you on. That's for sure.
Good. Have a good one, everyone.
Thanks, Teddy. Bye. Well, that was great.
Yeah.
I don't know if you saw Sherry, but he started with this just amazing video.
No, I was watching it down on my poster. I had my phone out, and I was trying to not ignore people at the posters, but that was really amazing. I just wanted to show it, saying, "Do you see what's going on right here?" And so, anyway. So we have someone else.
We do, and it's kind of a surprise, but I kind of let the cat out of the bag a while ago.
Okay.
A little bit.
All right. Spoiler alert. Yep.
Spoiler alert. Yeah. So Sonny did such an amazing job last time, and he hadn't started at NASA the last time we heard from him. He had just wrapped up his interview, and I think he was offered the job at that point, but he's officially started. So we figured we'd bring him on board for an update. So Sonny, are you here with us. Let me unmute you.
Unmute myself. Yeah.
There you go. There he is. There's the man.
Back in the conference room, are you?
Nope.
Nope.
Back in the living room, and the dog is.
All right.
The dog is. I have a dog now, by the way, as of 2 weeks ago. So Apollo is here running around.
Apollo, nice.
What else would it be?
Apollo. We'll see if he comes. Sometimes he just wants to jump on the couch. Oh, maybe.
Yeah.
Maybe. Here we go. There we go. Perfect. That's
Aw, cute.
Yep, you rescued him, and he's amazing. That's a pretty lucky dog. Little puppy. Yep, that's right. So we just wanted to kind of get a chance to find out how your life is going these days, now that you're officially at Johnson and in the ropes, learning the whole thing. So how's that going?
It's going well. More of my closet is taken over by NASA. So those are the only shirts that I own now. And I don't actually buy them from Center. I shouldn't say it out loud maybe, but Target's got a lot of nice ones.
That's a secret we already know. So
yeah.
we'll put that out on the next here.
So I prepared a few things. There's a few slides from last time, but I guess I'd go over kind of what's been going on the past, February 11th. So a little bit over 4 weeks, 4 or 5 weeks. We've been in what's known as FOD boot camp, and FOD stands for Flight Operations Directorate. So that's the directorate of NASA that plans for missions, trains for missions, and flies the missions. So that's our 3 words: plan, train, fly. FOD boot camp is basically where you go when you're an entry-level flight controller like myself, regardless of whatever your position is, to learn the general knowledge that you need of the International Space Station. It used to be shuttle. It was Apollo and Saturn V before, but now we're in International Space Station territory with commercial vehicles coming on. So boot camp is mostly focused on International Space Station systems. And when I say systems, I mean the system having to deal with power generation, the system having to deal with communications, the system that is my system, which is environmental and thermal controls. So you're learning about your system generally, but you're also learning about everyone else's system, because what boot camp is really about, besides just learning the technical things, is the soft skills: how to be a better teammate, how to be someone who can integrate with other groups and do it well. Because a huge part of the job is not just the technical part, but it's also being able to communicate effectively, receive and provide feedback effectively, and then take what you've gotten from feedback and apply it in your daily work experience. So I guess I'll share the screen for a second, and it's not really a well-made PowerPoint. I'm not there in my career yet where I can make one of those yet. So I've just got some scratch stuff put together. And I guess I'd go over, okay, so here we go. All right, so this is just outreach photos. What I wanted to show you guys, kind of a tag up from last time. So what I was working on as an intern was called Benefits for Humanity. That's a book that JSC is putting out now very soon. We just got the approval from the international partners and everything, so we're set on that. But basically, this is a book that you guys can read if you're interested in what does the International Space Station bring down to us here. And specifically the part that I was working on in the book covers things like the educational impacts of the ISS, the scientific impacts of the ISS, technological impacts, and then economic impacts is what we were working on. So learning about what kind of businesses has the International Station sparked. You know, the space station economy, or the space economy, the low Earth orbit economy, is now valued at something like $345 billion. So where does that come from? That's all in this book, and you can look at the trailer, and we actually have a trailer out, so you can look at that on YouTube if you're curious. And it was really cool working on it with my mentor, who the other L Space Academy is going to be hearing from this Thursday. That's him over there. If you look in that, I can't use my mouse, but it says Brian Dansbury, and that's my mentor. And so we basically got to sit down, and he's an aerospace engineer, and I'm a biologist. And so, of course, they gave us the section on economics, because that makes a lot of sense. So we got to learn economics and write this whole thing, and it was really cool kind of seeing my name on an official NASA publication. So hopefully that'll be out soon. And yeah, so that's the update on that. So, okay, all right, backtracking, back to boot camp. Whenever you go to boot camp, the first thing you'll get from your group is this thing called the training flow. And the training flow is referring to how you're going to get from boot camp all the way through to the flight control room, which you guys know is the room where everyone's got the mic on. And so I'll show you guys what mine looks like. And this is just for your first certification. And I'll slow me down, Sherry, if I'm not being coherent here.
No, you're good. You're good.
So basically what you guys see is the one person in the front room, the big screens, and there's one person per console. But really most consoles have what's known as a back room, which is where you start off. You still have a lot of the technical knowledge, but you start off in the back room. And to get in the back room, which is basically a support room. So let's say there's one person on console for Ethos, which is my field, which is environmental and thermal operation systems. One person sitting up front, and they have a lot to do. Well, there's someone right behind them double checking everything they do, providing feedback, listening to other communication channels between all the other consoles, all the other systems, and providing inputs to their front room controller. So where it says Ethos MIPSR, the MIPSR part basically means backroom flow. And where I am is on the top left where it says Common Content / Bootcamp. So that's where I'm sitting right now. After that, we'll go into basically my systems intro and then system specific knowledge. So what a few of these mean, this is obviously just Ethos introductory. And then, so here you've got temperature and humidity control, atmosphere revitalization, because a few of the things that our group does, so let's say atmosphere control system, well, you have to maintain a pressure inside of the space station. The cabin pressure is somewhere between 14.0 and 14.9 PSI. You have to maintain 79% nitrogen, 21% oxygen. So we do things like that, but we're also responsible for things like, let's see, Regen Eclipse. That's the system that connects to the toilet on the US OS side, the United States operation side. And so whenever we process urine from the toilet, we process that back into potable water. So that goes into the urine processing system, the water processing system. And then once we've got potable water, we do two things with that. We take some of that potable water and send it back to our crew members. And then we take some of that water and we can actually we can split the H2 from the O and derive more oxygen for the cabin that we can feed back into the cabin. And then now we actually have a system where we take that hydrogen that we split off from the oxygen and do electrolysis with CO2, and we can produce even more oxygen. So more water. So cool things going on all over, but it takes, each of these you guys can basically think is of one class. This is basically a class on thermal or temperature humidity control, and this is basically a class on the regen system for water and urine. And we've got a class, all about EVA. And then the interesting part here is if you follow this arrow, it takes you up to something called SimGates and mini sims and integrated sims. Simulations are exactly what they sound like. You're sitting in a flight control room, there's a flight director, and you are going through a scenario just as if you were sitting in the control room, and there's someone back there controlling the conditions that you're interacting with. So somebody might make your system go haywire, or cut comms, or station is now off trajectory. All kinds of things could happen that affect you, and it's to see how you react in that moment, how you apply your knowledge, and how you work as a team member. And so we have months and months and months of sims. I mean, I was told that the latest, so this is 71 weeks. I was told the latest that I would be out of simulation flow would be January 2021 at the latest. So this is, it's pretty constant, and it's tough, and it's a lot of stuff to know, but really this is almost kind of the easier part, because the communication and being a better teammate is huge. And there's a lot to learn there. So, and sorry about Acronym Central. I just saw someone say that. I'm really trying here to dumb out the acronyms, spell out the acronym, myself sound dumb. So that's our flow. That takes about 71 weeks. And we're just starting on that. Let me see what else I can think of. By the way, any questions anyone has that we can start off with those, and maybe I can go off on a tangent? I'll just look at the chat if someone's got questions.
Yeah, we can actually just put those in the chat. By the way, your Instagram following is going to blow up soon.
Oh, I had that on there because, that's right. Thank you. See, so whenever we had Sims today, let me show you guys something. And this is totally not to plug my Instagram, but if that happens in the process, then well.
Well, the Space Academy just followed you, so.
Okay. That works. So today we were in the White Ficker, which is the White Flight Control Room. It's a training room. And we had an audience back there, as you can see. People are constantly coming in and out. So when we were on console, we had a whole room full of people walking in and out every now and then on tours while we were doing our simulation. And I can kind of tell you guys what the simulation was today and how that applies toward our training. So as you can see, you're sitting on the loop system. The loop system is basically just a wired microphone jacked in to your console, and there are different communication loops. So there might be, and when I say loop, I mean basically a channel of communication between at least two people. So there might be a loop for the flight director. So whenever flight says flight ethos or ethos flight, they're saying, who are they talking to? Ethos, who they are, flight. I would jump on the console on their loop, on their channel, and I would say flight ethos, as in I'm here flight, what's up? So you're plugged into multiple channels and you're expected to monitor other channels that you're not on, because if your name is called somewhere else, let's say there's a loop with the power people and the comms people. But the comms guy is not actively in that loop talking, he's in some other loop. He has to know when he or she has been called in the other loop. So this was a really cool simulation, and the purpose of it was basically we have some rovers stuck on the moon. But the rovers are actually, well, they have people inside them. And there's a flight director, and we're given 75 minutes, and we're given all these constraints and objectives. And it's a low fidelity simulation. There's nothing really going on in the monitors. But your goal is, one, to keep your crew safe. That's always our first goal, is crew safety and FOD, Flight Operations Director. Let me just say it out loud. The next thing is our vehicle safety. So we can't keep the crew safe. We can't keep the vehicle safe. And then it's the success of the mission. So Moonbase is one of those simulations that you start off early on in boot camp. You do the first run of Moonbase when you're just learning how to communicate and how to use standard protocol when you're talking on a loop. You know, it's the protocol, by the way, is similar, I think, to other military places. You would say who you're talking to. So I'd say flight, if I'm talking to flight director, and then who I am, ethos. And then once they say ethos flight, I would know that they're there and listening, and then I can go on. So it's really cool. It kind of throws you into a whole new world, because we have people coming fresh out of college, like myself. I was an intern for a year, but basically fresh out of college. We have people who are ex-military, people who are teachers, people who have never done anything for NASA before. And so it's kind of like mind-blowing to come into that and expect to know all this protocol already. So we practice and we practice and we keep practicing over 8 weeks, and then over 70 weeks, and then every single day. So that's why the Instagram was up. Do we have any questions? I wasn't looking at it.
I'm thinking that not yet.
Any questions? Okay. You guys put them out?
Yeah, put them in the chat. Put them in the chat.
Okay. Let's see what else I got to talk about. See,
how do people get to the point of being able to go to the boot camp? Stanella wants to know.
How do you get to, okay. Well, as soon as you're accepted as a flight controller, you're in boot camp. And to apply to be a flight controller, there's no mysterious process. I could show you exactly how to do it right now, because it's really fast. So you would just pull up Google. You would type in NASA flight controller. And probably positions, and a bunch of jobs would pop right up. There's a bunch of places hiring. Contractors are hiring all the time. There's some civil servant positions that open up, but basically you would look anywhere else you would look, right? Like there we go. So there's an ISO flight controller job right there with Geosystems, and you would apply for the position through there. So we've had a lot of people come on straight from college, and this is, everyone goes through the same process to apply, whether it's through USA Jobs, which is if you're a civil servant, a government employee. If you're a civil servant flight controller, you would go to usajobs.org or .gov, I believe it is .gov, and you'd build your resume and you would apply for the position. Contractors are a little bit different in how they hire than government employees like civil servants, but it's all the same kind of, it's the same job, right? It's a badgeless environment. So I'm wearing a badge that says that I work for a contractor, but when we're in the flight control room, when we're teammates, when we're working side by side, there's no such thing as a contractor and a civil servant. You're all doing the same job. You're making the same pay basically, and you're all there for the same mission. and to keep your crew safe. So if you get accepted as a flight controller, you're in boot camp.
So there's a question about citizenship. Do you have to be U.S. citizen as part of that?
I believe you do, right? Because some places in NASA are restricted to U.S. citizens only, like Building 9 is called our Space Vehicle Mock-up Facility. So a lot of your training happens there. And because you're handling often sensitive data, that kind of stuff is restricted to U.S. citizens. Kind of like the internships are, sometimes they're restricted to U.S. citizens. So I believe for flight control that they're all limited to U.S. citizens only.
Right. And that would have been my guess too. It's ITAR, basically, which is restricted. Can a flight controller learn their way to becoming a flight director, or I guess learn their way or earn their way for a mission, or is that separate hiring process?
Yeah, so NASA every now and then puts out kind of like a hiring thing for flight directors and also for astronauts. So astronauts are, I think every year, every other year, something like that, we put out for astronauts. And flight directors we do, I'm not sure how often, but pretty frequently. They only accept maybe 1 or 2. This last round, I think, and I might be wrong, but I think it was the first time that we had a flight director come in who was not previously a flight controller. I think that person was military and they transferred over with no experience in NASA, which is interesting because the position is essentially you need to know a lot about the ISS systems in general. Your flight director is kind of a generalist. They need to know the high level of what your system is doing in that moment and what all the other systems are doing in order to make an assessment based on the situation. And they need to have situational awareness of everyone's console in general. So coming from outside the organization makes it difficult. I'm pretty sure most of our flight directors have been flight controllers before and successful flight controllers, whether it's through Space Shuttle, through International Space Station, or they went from the Apollo program into Shuttle or something like that. So you do a separate training flow to become a flight director. And usually you would start off as a flight controller and then maybe something like a mission lead or group lead or something like that. And then with experience, you would be able to apply for a flight director position.
Okay, and then Matt wants to know, and it's an interesting question, especially if you've ever watched Apollo 13.
Mm-hmm.
So are the trainings staggered with anomalies in some trainings, or does, where something goes wrong and they throw it at you and you have to think your way out of it? Or is it just all choreographed to be plain stuff, good stuff in terms of that?
No. So your simulations are staggered with that stuff all the time. Whenever you're doing simulations, that's the whole point of a simulation, is you can think of it as like an Apollo 13 all the time. Something's going to go wrong in some way you probably can't predict, and you may not always be able to handle, or several systems will go off. So we do that in simulations all the time. And I haven't gone through the sim flow very much, but even just in Moonbase, you're drawing, in Moonbase it's a low fidelity situation, but we have rovers. And so there's things that can go wrong with rover operations. And so let's say your rover has a malfunction, it's stuck for 5 minutes, and everyone's launching off the moon in T-minus 4 minutes or 6 minutes, right? So you have a minute after you're done being stuck to get back to your launch pad.
And you're talking about human rovers, not the kinds of things. Yeah, people who are in
sure.
rovers.
Sure, human rovers, or you could, if you want,
astronauts in a mobile situation.
Yeah. So they call them rovers, but it's essentially crew members. You're inside the rover. And so things go wrong in simulations all the time. And they do that to see how you're going to respond to stress in the moment. That happens, if you guys remember, I talked about the interview. That happens throughout the interview. That happens throughout the entire training flow, because you're going to have a bad day on console sometimes. You hope that it's just good days, but you are always planning to handle something like that in the moment. So their training is definitely staggered with things like that in simulations. And in the classroom, it's always put upon you, how serious your job is. And even in simulations, if you find a way to kind of, well, they didn't say I couldn't do this, that's not the point of a simulation, right? The point of the simulation is not to try and cheat the system or game the system. It's to play the game correctly and play in the moment and do the best you can. And sometimes the best you can do is not enough. But part of what, and I'm wearing it on my badge right now, sometimes the best you do is not enough, but there's a part of the FOD Flight Foundations that says to always be aware that suddenly and unexpectedly we may find ourselves in a role where our performance has the ultimate consequences, and to recognize that the greatest error is not to have tried and failed, but that in trying, we do not give it our best effort. So that's what they're trying to instill in you from day one. And that happens the second you walk in. So that's a good question. They definitely make sure that we're stressed correctly.
Well, it's funny you mentioned that, you can't game the system. All I can think of is Star Trek and James Kirk and Kobayashi Maru, which is where he, in his academy, tried to game the system and got away with it. And actually, there is, not too far from your apartment, Sunny, there is a Kobayashi road that I've always
Yeah.
it's
like
somebody wanted to kind of put that in close to Johnson Space Center.
down the street.
Crossed my mind. You cross it all the time, going back and forth the way you do. Anyway, I think it's pretty funny. So in terms of, I'm just looking at the questions too. What's the biggest lesson? This is Kristen. What's the biggest lesson you've learned so far in those situations, in terms of those anomalies?
Yeah, one of the biggest lessons has got to be active listening and communication. You can know everything about the situation, but it's useless if you've told no one else. You're just one Lego in the entire piece, right? So if you're not communicating to everyone else, it doesn't matter what you know. So in our simulations, there have been times where, let's say something goes wrong with my system. And it's something that no one else knows. My flight director, for example, my control person doesn't know it. If something happens with my system and it's a complex situation, I have to be able to clearly and concisely pass that on to my flight director so they can inform the rest of the systems and have situational awareness of what's going on. The technical things, I've got a back room or I've got a partner in that situation to help me. I have the other rovers for input, but they're useless if I can't communicate that. And if another rover is saying something, and remember, this is a dynamic situation. So if it's a simulation, that means there's other things happening in your system and all kinds of other things happening right outside your system that mingle with your system. So if someone else has a problem and I'm not paying attention, that's a failure on my part for being an active listener. It's been huge. I've had plenty of times where I've like kicked myself for why did I not ask that question? Just today we had a situation, for example, our flight director came on and she was basically given a contingency, a card, like a condition card, kind of like a board game. She was given a card by one of the instructors that said that all of the rovers were going to have a malfunction and that none of the rovers could move for 5 minutes. And one of the rovers, right, with people inside of it, was essentially a mechanic, a repair person, and they can go around fixing rovers. We were told, okay, all the rovers have a malfunction. So everyone's freaking out because we have to accomplish our mission and then get back to the launch pads. At no point did our rover or any of the other rovers jump on the comm loop and ask, is there a way to have this malfunction repaired? Because the way the malfunction happened was after that first 5 minutes, you're good to go. You continue moving. And in this board game, the way you're moving is using 2 dice. And every time you would roll 2 of the same numbers, if I rolled 2 6s or 2 4s, my rover is stuck for 5 minutes again. And I can't do anything. And I'm losing time against the clock. At no point did we get on the control loop and say, control science, we're a science rover. Is there any way that our rover can be repaired? We thought it was just a software malfunction that was just going to be there for the rest of the mission, which was false. We wasted 15 minutes getting stuck 3 times when we could have been repaired by the repair rover way before. So there's just times where you don't ask the right questions, or if you have a question, you're probably not the only person who has that question. And it's really hard to kind of put yourself in that mindset because you think everyone else around you is smart and you're the one lost. And if you just give it a few more minutes, you'll catch up with everyone else. And that is not the way to think of it. Everyone here is really smart, but we're all human and we're all going to miss something. So if you don't ask the question, or if you just make your communication too brief, because we're taught to be very verbatim and not verbose, don't go on for too long on the loop. Because if I'm talking on the phone and you're trying to talk on the phone at the same time, no one can hear anyone. So if you're not communicating effectively, it doesn't matter what you know because it can't be applied.
Okay. There's been some chat about what the rovers were and whatnot. So from Vincent, what habits, questions, and actions do you use and take before entering each new project?
Okay. And what were those three? It was habits, questions, and actions, right?
Yeah. Mm-hmm.
What habits? So one thing that I've had to fix is because it was never a habit for me growing up is honestly to prepare and kind of like pre-brief and just remember what I'm going into. So it's kind of sitting down, understanding what I'm getting myself into. And I'm one of those people who gets in the shower and talks to himself a lot, runs up the water bill. So I will sit in there and review forever what's about to go on, review possible conversations that are going to happen in a simulation, things that could go wrong. It's baking in my head for like 2 days before it happens, if it can. So my habit now is just to prepare more instead of less. Because I used to kind of like being stuck in a situation where I'm not prepared. And so I have to wing it and my blood pressure spikes and I've got a bunch of adrenaline. That's not where you want to be in a situation like a simulation. Nobody crosses their fingers whenever they're doing this stuff, right? So preparation is huge. Questions I ask myself is also related to preparation. Am I ready for this? Do I need to call someone and just honestly admit, and part of it's being vulnerable and honestly talk to someone and say, I'm not ready for this. Or can you help me on this? Even if it's my system and I'm talking to, let's say I'm Ethos and I'm talking to the power guys. It's okay for me to ask the power guys if they know something about my system, even though I should know it. We can talk about why I don't know it later. First of all, let's communicate this back and forth so I know it now, and then later you can grill me on it. So it's asking questions of myself and then asking questions of my team members, and making sure we're all on the same page, making sure we all have the same plan. Today we had some problems where we weren't all on the same page, and that caused one of our crew members to be stuck on the moon after the time elapsed. So we had 4 crew members in rovers, 3 of them got off the moon in the launch time, 1 person was stuck. So, in these simulations, you're going to kill people, right? So that's something you have to deal with. And I'm a core system. And what that means is there are 4 core systems for the International Space Station, and they make sense if you think about it. Power, you always have to have power. So that's the Spartan console. Comms is Cronus. You always have to have communication up and down. Ethos, which is life support systems and emergencies. You always have to have those to have humans inside. And then ADCO, which is attitude and trajectory for the International Space Station. So that means that one of us, all 4 of us are always in mission control 365, 24/7, right? Always. And there's a flight director and a ground control flight controller. And so we're always on watch. And if someone is going to get hurt, it's usually going to have to do something with one of our systems. And so people will die in the simulations, and you're kind of thinking about, okay, yeah, I just killed someone because I messed up. And I come from EMS, and so I've had some experiences in that. Not a fun place to be mentally. So, some of the actions I do is after something like that happens, like after today, after we left someone stuck on the moon, even though my system, I thought that we did everything right, I wasn't the flight director, right? So, but at the same time, I'm not going to put that just on my flight director. They were just working with the inputs. They might be the builder of the Legos, but if the individual Legos don't say what order to go in, then we're stuck. So there's no blame to go to just one specific person. It's a team effort. And one of the actions that I do is a debrief, right? Just we debrief as a team, but then I go home and think about it and think about what I did wrong and how to improve from there. So it's nothing special. It's just kind of what seems to be natural and what's been working so far. Hopefully that answered the question without going off on a tangent.
Well, that's good. And Kristen mentioned that you mentioned something about the rover launch. Do they launch from the surface of the moon or Mars? I didn't catch that.
Yeah, this is nothing. Here, I can show you. This is nothing super confidential. It's just this is essentially, I want you to think of this as your moon, right? And there are 4 rover types. And when I say launch pads, these are the places that we see the green boxes. So they're equidistant from one another and they're starting off right there. There are 4 rovers and they all start from a green launch pad. So let's just say there's a mechanic. There's one person who collects supplies. And so if you saw those multicolored boxes all over the map, Those are supplies. There's one that is a lab rover. So there's a moon base. That's why it's called moon base. So we're getting to this moon base. And there's a science rover. So that means there's some science depots around the moon. And every rover has their own mission objectives. One of the primary objectives is, even though we're all starting down here, we're all supposed to touch moon base. Lab is responsible for opening moon base, closing moon base. And then within a certain time, we have to make it down to the launch pads. And the launch pads aren't just ready to go. The way you activate launch pads is by achieving objectives. So if moon base is opened and everyone touches it and such, then you gain launch time on pad so-and-so. And to launch one rover, it takes 2 minutes. So if we have 4 rovers, we need at least 8 minutes of total launch time. Or I think it's 6 minutes because you can launch at T0. So the whole time you're playing this, you're weighing the odds in everything you do, because sometimes your rover can get stuck, like mine did 3 times. So on 3 separate occasions, we rolled doubles. And this is as we're on the way down to the launch pad, and there's like 10 minutes left before the simulation's over, and we missed the launch. And we rolled doubles. And we're just sitting there like twiddling our thumbs, just kind of like, wow, we're like 6 paces away from that grid and we're stuck. So we made it off, but it's just everything kind of comes down to the wire. So it's a low fidelity simulation, right? It's nothing like flying an International Space Station. At the same time, it's a lot like flying a space station when it comes to communications and how you're talking to people and the protocol that you use. So they start you off and they start you off from small things and move you up to bigger things. And that's the flow of boot camp as well. You're starting off with general systems knowledge. You have exams just like you would in school. A lot of our days have been come in 8 a.m. I came in 2 weeks ago at 8 a.m. and I'm a biologist, right? So this was funny because I came in 8 in the morning with half of a Folgers cup of coffee in my hand that was way too hot to drink. So I haven't had any. I sit down and I look at the board, and we're doing orbital mechanics of the International Space Station at 8 in the morning. 2-hour class. It was super cool. But the girl next to me is an engineer, and she kind of turns to me and she's like, "So you're a biologist, right?" And I was like, "Yeah." She's like, "So this is super fun for you." And everyone basically knew that I was a little bit lost, because I'm the only guy who's not a physicist or an engineer. So it's like a biologist and then aerospace, mechanical, chemical, petroleum, blah, blah, blah engineers. So that's been fun. But they take you through the flow in what I think so far has been a really cool way. You're starting off with general knowledge of everyone, so you know where you fit in the puzzle, and then you're learning more about your system. You're learning from a small piece of paper up to an International Space Station, basically. So I really like their training flow so far.
All right, that's good. And just thinking about your experience and getting the chance to do what you did, one of the things I want to talk about for a second is when you do an internship and you have the chance to go and be at NASA for a series of weeks, either it's summer or one of the semesters, what beyond that particular job do you get to do? And I'm thinking about you in particular, how many people you got to actually talk to and go to presentations about, but also network and eventually landing your job. So can you talk about kind of the experience that you get during an internship in terms of all the other opportunities you can take advantage of?
Yeah. So I can speak for Johnson. When you're here at JSC as an intern, whether it's a contractor intern, whether it's an intern for I was program science office, you might be in the flight directorate, you might be in the human research program area. All the interns have the same opportunities as far as hearing lectures from astronauts, lectures from flight directors, lectures from scientists who work in novel parts, things I've never even heard of, human research, designing things for Orion. You will have opportunities to hear from all kinds of amazing, interesting, and very smart people. You'll have the opportunity to just walk into one of our lunch buildings. So we have two cafeterias, building 3 and building 11. You could walk into a cafeteria and see an astronaut who was in space a week ago. Opportunity to talk to anyone. Were you talking to me, Dan?
Yeah, you just cut out for a second.
Oh, sorry. So
no, it's fine. It was a split second.
Okay. Maybe it's my fan. So you can you have a lot of opportunities to talk to people just like astronauts and people like that. But of course, you're working in your directorate. You're working whether you're in flight directorate or in the science directorate, like I was for the station. You are constantly interacting with managers. You're interacting with people who are looking for someone who would fit well at NASA and in their department. So every day you're at work, you're trying to not just do a great job, but kind of let everyone know that you're doing a great job. If you're not good at, owning your stuff and saying that, hey, I accomplished this, get better at that. Kind of get better at letting people see that you're a contributing member of the team. My position made that kind of obvious for me, but there's friends of mine whose positions aren't so obvious because they're in engineering and they're always working as part of a team, and the end product has involved, 30 different people. But if one of those, the steps to that product didn't happen, then the product wouldn't have happened. And they were one of those key steps. So you have to point out what you've been doing. Don't shove it in someone's face, but you're trying to just bring up the fact that you're a contributing member of the team. You have all the chances in the world to make sure that people know that you're here and doing a good job. So you're interacting with managers, you're interacting with astronauts. Let me see who else you're talking to. Tons of contractors. So NASA is split. I'm not sure if you guys have been told this, but it's split between contractors and government employees, civil servants. And so there are new contracts and new contractors all the time. And those contractors are also looking for new personnel. So you're interacting with people, not just civil servants like the NASA managers, but also managers for general contractors for things like the IMOC contract, which is Integrated Mission and Operation and Control, which is mission control contract. Human research. Anything you can think of probably has a contractor involved. Even our cafeterias are run by contractors. So literally everyone you're talking to is someone who may throw you an opportunity to get a job. And how it happened for me was just, I came back. So let's go back. I came at JSC in January of 2017. I delayed graduation. And then it was coming around to May, and we're working on the benefits book that I showed you guys. And I really wanted to stick around, and I was doing a great job. So I asked to come back, and I delayed graduation again. And then it's getting through that summer, and I probably shouldn't ask, but I ask anyways. And I'm like, hey, can I come back again? And so they have me back again. And at some point, my manager kind of comes up to me, and he's like, where do you want to end up? I mean, you're supposed to be rotating to other, internship positions throughout the center. So you kind of get a taste of different departments. And he's like, you've been here for a year. We love you, but where do you want to end up? And so I was really honest, and I got to just say like mission control, like operations. I've never done it a day in my life, but it'd be really cool. I think, I'm not sure. It might be cool. And so he heard that part of it, and he was like, well, go talk to someone. Here's a friend. Go talk to him. Ask him what his day is like. Ask him if he thinks that you'd be someone who'd be a good fit for that job. Because I didn't know if that's something I wanted to do, right? I've always had trouble being in an office job, and that's one of those jobs where you're in the office a lot. You're sitting at a desk a lot, you're working problems, but you're not getting a lot of your outdoorsy time when you're at work doing that stuff. And that kind of stuff stresses me out. So I had to make sure that I could at least handle that and some of the other stressors that come with that kind of a position. So I got to go talk to someone who had done it for 20 plus years. And that's normal. I mean, they're happy to talk to you. Everyone is happy to talk to you. Almost no one is going to say, hey, I don't have time for you, go talk to someone else. So, yeah, you have opportunities all the time to talk to people who you think you should have no access to, but for some reason you do.
Well, and we're getting some comments about, just being able to hear what you're going through and some of the questions you've had and the doubts and things. It just helps it make more real the experience and the possibilities for a lot of the other students in the academy. I think it seems so ominous to try and think about how do I apply for NASA and how could I ever get a job there, and it is. It's just interesting. Now they're wanting to know, do you even have time for hobbies? And I know you have dogs, so you at least have a new.
So I'll say something before that. I'll say something on that part about, how do you apply to NASA and stuff like that. Guys, I was pretty confident back in January 2017 that by May 2017, I was going to be unemployed and applying for graduate programs. And then by May 2017, on my calendar, it was pretty much like, okay, in August, after the summer's over, I'm going to be unemployed again. And after August, I was like, great, I get to end out the year here, and then I'm going to be unemployed again. there was never a point where I was like, you know, I'm for sure going to get a job here. From the first day, I was like, I never want to leave this place. And then every single day for that entire year, I was like, I can't believe I'm not going to stay at this place. There was never a moment of like, I'm sure I actually belong here and someone's going to keep me here. I did great work every day just because it was something that, just like the previous speaker said, it's something that no one asked me to stay overtime for. No one asked me to stay at night for. No one asked me to keep pushing for, but I loved it. And, you know, it's, if there's any of you who've been in the military, you kind of feel that honor toward your country, like that, wow, like I'm giving back to my country. And NASA is one of the coolest ways to give back, I think, to the next generation, to the current generation and the next generation, and kind of honor the previous generations. And so it's just something that I love to do. So just follow that. I mean, there's never going to be a clear path. I really thought I was not going to be here. I had no idea I was going to be here, for sure, a year ago. And then when it comes to hobbies, not really. I've had time for hobbies. So I weightlift. That's all I've really been doing. That and learning how to train my dog has been a hobby, and learning how to be an active listener in my relationship has been a hobby. So I'm better at that.
Well,
That's an important one.
Lifelong hobby. Yeah.
Yeah.
Yeah. So, yeah, besides that, not really. I've just been kind of stuck learning all this, not stuck, but just, you know, I've just kind of paused everything, and I'm pretty sure I don't want to go and take a vacation this year or anything. I just kind of want to stay glued in, because in your training flow, so I'm just one of the new hires for the Ethos subsystem. I have 3 teammates basically who are in the certification flow with me that I showed you. So we're all going through that flow. So my job is, in my brain, just to kind of stick around, and so we can all pace ourselves through it and go through it as a team. Our number one priorities are ourselves, as we've been told, but we're still one team, you know, going through the whole flow, and we can all help each other. So if I was off track, or if I go to do a vacation or get too involved in a hobby, I just don't want to be left behind or leave someone else behind. So I'm just kind of trying to press pause and prioritize for right now. But you have plenty of time.
I want to remind everybody too that, you know, half of NASA is going to be graying out, retiring. So there's going to be a lot of need for replacements. Every time I see scientists, even here at the conference, and I'm talking to them, and they say, well, what are you doing these days? I said, I'm training your replacements. And, you know, these are a lot of old people that are getting ready to retire that NASA's going to have, that we call it the silver tsunami. And they're really serious about it. That's why we're running the academy. And that's why they're looking at ways to get people involved and start thinking about career pathways that are going to be leading this direction. So, you know, this is an important, serious step. And Sunny, what you're saying is you're all in on this, and that you don't mind not having all kinds of discretionary time, because you really see this as a passion, and you're following it and putting your time in.
Yeah. And it's kind of, you know, when people, okay, there's 60 people here right now. At least some of you are going to end up here, and some of you may even end up as my bosses. So
it's especially the ones that stayed long, right?
yeah, especially you guys. If you can tolerate listening to me for this long, you'll probably do well in like all the meetings you're going to have every day, where you're just like, oh, this. But anyways, well, I lost my train of thought there, didn't I? You were saying something there, and then I lost it. Man, so
no, you're all in. You're all in. Somebody wanted to know if the other people in your cohort that's with you are all biologists, or are they different stuff?
No, so there are 50 people in boot camp, and there's 20 total positions beside flight director, I think, console positions. And if you guys are interested in what those positions are, you can just go on Wikipedia, like just type in on Google ISS flight controller positions, and there's a Wikipedia that breaks everything down from now, 2010 to now, all the current positions. So we have, let me see what I remembered: electrical engineering, chemical engineering, mechanical engineering, lots of mechanical engineering, physics. So all those people are either physics, or there's like 2 physics people, and the rest of them are engineers. And then there's a biologist. So yeah, there's no other biologist there. That's about it.
Okay, and you just answered Mathilde's question. Is there any double E's in there? You already mentioned that there. Yes, there is. All kinds of different people.
Yeah, and they're not just involved in disciplines that involve electrical engineering. There are people who are involved in things like, let's say, so Spartan's going to have a lot of electrical engineering, right? Spartan is the power systems. So obviously there's electricity all over that. Ethos has some, we're the internal thermal control system, but there are console positions that have people who you would be like, how'd you end up there? The point of hiring engineers and people with hard science degrees is that they're not looking for someone who is a one-to-one fit for the job. Like, oh, you're an electrical engineer, so you would do great in, external power systems and batteries. It's to show that you're capable of getting a degree that requires some intense level of rigor that took you at least 4 years to get. You stuck it out, you did well, and you're capable of sticking through a tough training flow. Because that's basically what your college is telling you, is that you went to a training flow, you stuck the training flow out, you got your degree. And that's what your job as a flight controller is going to be. You're literally getting paid to learn. I mean, I'm working with people who every day we come to work, whether you're an intern or you've been there for 30 years, you're carrying a backpack on your back. So we could attest to that. I mean, everyone's carrying a backpack. You're literally going to school every day and getting paid for it. So yeah.
Well, I know that we could keep you on forever. I know you've already had a long day, and it was really great for you to stay on this late with us. But we should let you go so you can get ready for your tomorrow session. And we've kept people here long tonight too. So we want to thank everybody for coming in. And Sunny, thanks again for coming and just giving us an update and seeing where you are. And how many followers do you have now?
I'll have to double check. Hopefully not that many more. I'm not that interesting.
Well, I think you better work with Dan and get more interesting there.
Yeah, no, there's quite a few. Wow, okay.
No, you got a whole bunch.
Cool.
Yeah, at least 25 or something. So
hey Dan, we'll have to post on the Academy one on Thursday that they can follow Sunny too. So you'll have links more there too, Sunny. So
yeah.
Well, it was great hearing from y'all. And if there's any other questions, you can get my contact from Sherry. I'm also not perfect at answering emails on time, but if it's something like, if you're definitely trying to get into Johnson or you got a position at Johnson and you have questions, shoot me an email and I'll try to help you out.
Well, now they're going to slide into your DMs.
Yeah.
Right. Yeah. No, sorry.
Oh goodness. Well, anyway, we appreciate you coming back and helping us out. And it's just not quite the same at LPSC here this week without you here, Sunny. So
that's right. Yeah. If you guys remember, I met Sherry at LPSC. What was that? 4 years ago?
4 years ago. 4 short years ago.
Yeah. So it's cool that she's back in town for that.
Yeah,
I know. I was trying to make it out there, but I have this thing called the job, and it really makes life difficult.
Well, it's a long ways. It's a long ways too. We do have 4 LeSpacers here this week, so we actually have some of our academy here. We've been meeting up with Jessica and I, and spending some time, and I'll be doing a LeSpace poster next Thursday or this Thursday. So we'll be talking all about your project. We're pretty excited about all the things and the results that are coming out. We're bragging about y'all. So it's going to be fun to keep us going. Also, Dan, did you talk about the next?
No, we have not talked about that.
Okay, well, let's wait until we get back for everybody next week, and we'll make sure we bring that up in terms of the next invite, special invite for Academy 2 that's going to be able to have a different forward going in terms of another offer for another academy if you're interested. And we'll be talking about that more next week.
Yep. And just a reminder, I put it in the chat a while ago, but submit your team's PowerPoint with your updates. That would be much appreciated. You should have your fabrication done, if not done already, wrapping up this weekend. If you need a couple extra days, we can arrange that. Internships, we talked about that a little bit earlier on before we started, but we're still waiting to hear back from a couple mentors. So not all final selections have been made. So there's still hope.
Yeah, we still have the ASU ones that are going
yes.
to. We've been letting everybody else select first, and then our ASU ones are going out. So
yep, and that's
still some good possibilities out there.
Yeah.
All right.
So,
And so I'll let you answer for Mario there, Dan, as we say goodnight to Sunny.
all
And
right. Thanks, Sonny. Appreciate it.
Yep.
Thanks, guys.
All right. Say hi to Nija.
Yeah, I'm gonna say hi to you. Hey, hi to Mom for you right now, and then I'll say hi.
Hey. Hi, Mom.
And Mario, go ahead and shoot me an email on that. We'll get you set up.
All right. Good night, everybody.
Good night, everyone.
Safe week. We'll be
Buenas
back.
noches.
Yeah. Okay. Good night.